We're approaching the end of the section of this course when I'm talking about entropy and its applications. Today is going to be a more theoretical video, probably rather a short one, although I always underestimate how long they're going to be when I'm starting them out. And then in the next video, well, possibly two, depending how I decide to do things. I'll give another couple of applications of something called Shearer's entropy lemma, which I'm about to talk about now. Just in case you're curious, that sort of banister at the, not banister, the banner just behind me, it's because I have a son who became a teenager today, so it's a form of celebration. So before I talk about Shearer's lemma itself, I want to talk about a result that maybe looks as though it ought to be obvious, or at least have a very simple proof, but I actually can't seem to find a very simple proof. And I have some reason to think maybe there isn't one. So I'll talk about that in a moment. But the result is called subadditivity. Let's call it subadditivity of entropy. And it's just the basic fact that the entropy of x and y is less than or equal to the entropy of x plus the entropy of y. And that's equivalent to saying that the entropy of x given y is less than or equal to the entropy of x for any x and y. That's just by the additivity rule. You can rephrase this in this way. It looks as though there ought to be some, simple deduction of that from the axioms, but at the moment, I don't see a way of doing it actually that doesn't use the formula. And also, I've sort of looked up proofs, and they seem to use the formula, and so I'm going to use the formula. But if anybody does spot a nice simple trick, then I'd be very happy to hear about that. But one slight reason to think that maybe, just maybe, there isn't a really simple proof. Let me just give an example. So supposing I have a distribution that, let's say, x equals 0 with probability something like 0.999, and is uniformly distributed on 1 to 100 with probability 0.001. So in that case, we get that the entropy of x is going to be, well, we can probably work it out. It'll be 0.999 times 1 over 0.999 plus 0.001 times 100 times log of 1 over 100,000, I think. I may have got this wrong, actually. I'm just suddenly sort of decided at the last minute to do it rather than... But whatever it is, it's not too big. Basically, although there are quite a lot of numbers here, the probability that we end up here is sufficiently small that we're not going to get a very, very big entropy. But, so this calculation, as I say, may be completely wrong. But the rough point is that because we're most likely, we're really very likely to be, it's sort of pretty close to being a distribution that's just, or a constant, a random variable that just is a constant value. It's just this small chance that it is uniformly distributed on this set. The entropy is not very big. But if I now define y to be 0 if x is 0 and 1 if x is here, then it's possible that when I condition on a value of y, in other words, well, in fact, it happens. If I condition on y being 1, that tells me that x is uniformly distributed on 1 to 100. So for some values of y, the conditional entropy of x, given that y equals y, or given that y equals that value, is much larger than the entropy of x itself. So what we can't say, we definitely can't say, and this bit is correct regardless of what my calculations here are, so it's definitely not the case that the entropy of x given y equals y is always less than or equal to the entropy of x. But what we do find is that on the occasions when this is bigger, it tends to be the case that the probability that y equals y is sort of small, and that cancels out the, or sort of balances out, or more than balances out the effect. So that somehow is an indication for me that a really simple proof probably doesn't exist, and that maybe you've got to use something like Jensen's inequality, which we are going to use. So let's just write out, we'll say that x takes values in A, y takes values in B, probability that x equals A is PA. These are similar notations to the ones we've had already. Probability y equals B equals QB, and the probability that x equals A and y equals B equals PAB. So now let's have a little expression for the entropy of x given y, the conditional entropy of x given y. It's the sum over all B in B of QB times the entropy of, I'll do it in 2 steps. So the entropy of x given y equals B. And now let's expand out that second bit. So it's the sum over B QB times the sum over all A of, so we're inside the part where y equals B. So we add all the PABs divided by QB and take log of QB over PAB. And now we just got to manipulate this a little bit. When you're wondering, this is one of those calculations where you don't really have to remember it, you just have various tricks. So one of the tricks is obviously we're going to interchange the summation at some point, so let's just do that. So I'll do that. I'll do the whole thing in several steps. So the sum of A, sum of B, and then the QB's cancel, so that's quite helpful. PAB log QB over PAB. Now let's just think what we're trying to get. We're trying to compare this with the entropy of x. And the entropy of x is going to involve PA times something or other. So let's sort of insert a PA with a view to getting the entropy of x to pop out at the end of all this. So I'll put a PA there. And then I'll get PAB over PA log QB over PAB. And at this point, I spot that for each A, the sum over B of PAB over PA, that's basically the sum of the probabilities that Q equals B and P, and X equals, sorry, Y equals B and X equals A, given that X equals A. So those add up to 1. And that's a concave function, so we can apply Jensen's inequality and say this is less than or equal to sum over A, PA. I'm applying Jensen's inequality to this part here. And I'll get log of sum B PAB over PA times QB over PAB. And that equals, well, we can cancel the PAB with the PAB, but also the sum over B of QB is just 1. So that works out as the sum A So first I cancel those, and then I observe that this sum over b cancels, and I just end up with log 1 over PA equals hx. So if you use the formula, then it's just a little bit of algebra and we get the result. So that's the first thing I wanted to do. Second thing I want to do is an immediate consequence of that, which is that we get that the entropy of x1 up to xn is less than or equal to entropy of x1 plus entropy of xn. And I won't insult your intelligence by writing out a full proof. It's just the obvious induction argument using, where's it gone? Using this statement here, the subadditivity for two random variables, as the base case. And so that's result number 2. And result number 3 is an interesting generalization of this subadditivity. Just before I talk about that, I'll just mention one quick definition, which is called the mutual information. So the mutual information of x and y is defined to be the entropy of x plus the entropy of y minus the entropy of xy. So roughly speaking, it's some sort of measure of how dependent x and y are on each other. So if x and y are completely dependent, say x equals y, that'll give us the entropy of x plus the entropy of y, and then the entropy of x and x will just be the entropy of x by a simple argument using invariance, and we'll just get the entropy of x. So that's sort of saying that x and y would share their information completely. And at the other end of the spectrum, if x and y are independent, we'll get the entropy of x plus the entropy of y minus the entropy of x plus the entropy of y, all in brackets, is 0. So the mutual information when they're independent is 0. When they're utterly dependent, it's the entropy is the entire entropy of x. Notice that we can write that as also as the entropy of x minus the entropy of x given y, or the other way around, the entropy of y minus the entropy of y given x. Right, let us move on. So now I want to talk about a result that has many applications in combinatorics, and this is called Shearer's entropy lemma, as I said earlier. And I want to state it as follows. So I have a random variable which is made out of some other random variables. And these random variables here may well have lots of complicated dependencies on each other. And it becomes an interesting statement, in fact, only when they do have dependencies. And I'm also going to say, let S be a random subset of 1 up to n. And suppose that for each I, the probability that I belongs to S is greater than or equal to mu. So we've got some mu, we've got a random subset of n, so S we can think of as some sort of random variable or whatever, but and then I will belong to S with probability at least mu. And then the statement is, but then one piece of notation, we'll write, so if S equals I1 up to IK, we'll write just a nice useful piece of shorthand, XS for XI1 up to XIK. So it's that random variable. And then the entropy lemma says that mu times the entropy of X is less than or equal to the average over all S of the entropy of XS, which is a rather natural looking formula, but you know, the entropy's got all those logs and things like that, so it's not actually, just because it looks natural, it doesn't mean that it's a complete triviality. But it turns out to have a really rather nice proof, which is not Shearer's original proof. If I remember correctly, proof is by Jayakumar Ramakrishnan, who's the same person who came up with a beautiful entropy proof of Bregman's theorem that I gave in the last video. So let me show you how that proof goes. So first of all, we'll just note that the entropy of XS, so I'm just thinking of S as some random set chosen according to this, whatever the distribution is. Usually we take actually a rather simple distribution, like all subsets of n of size k or something, and then mu will be k over n. But in principle, it could be any distribution. So I've chosen something of that form, and I'm denoting it as xi1 up to xik. So i1 up to ik are also sort of random as well. But leaving that aside, so that equals by the chain rule. Oh, and let's, we'll say that we, by convention, we'll always assume that I1 is less than I2 is less than IK. So what I was writing here doesn't depend on that assumption, but I do want to make that assumption. So it's going to be the entropy of X1 or Xi1 plus the entropy of Xi2 given Xi1 plus ... plus the entropy of xk, no, xik, given xi1 up to xik minus 1. And now let's introduce a little bit of notation, and then we'll have an inequality. So well, actually, I'll write the inequality. It's slightly nicer, a little prettier on the page. So that's going to be greater than or equal to. So what I'm going to do here now is just condition on more things. So here I'm conditioning on nothing. I'm going to write this as h x I1 given x less than I1. So I'll just say what I'm doing here. This less than I1 is meant to be shorthand for x1 all the way up to xi1 minus 1. So it's just all the random variables that come before I1. But I'll write that down in a minute. So plus all the way up to h x I k given x less than I k. So this is very important that I ordered I1, I2 up to IK in the right order. So that means that when I condition on everything up to IK minus 1, I'm conditioning on a strict, well, on a superset. I'm conditioning on, I was already conditioning on, I'm not conditioning on, sorry, what am I trying to say? I'm conditioning on all the variables that I was conditioning on before, and possibly some more. And so the more I condition on, the smaller things get. And by the way, that was not a completely trivial remark, because it depends on the subadditivity that we've proved. So let's just quickly remind you that conditioning on some stuff makes the entropy smaller, but until I proved the result I proved before, we didn't actually know that. It might look like the sort of thing that we knew, but in fact we didn't. So I'm using subadditivity in order to get this inequality here. So now let's take, so let's just quickly where x less than I means x1 up to x I minus 1. It's just another piece of shorthand. So now take expectations over S, and what do we get? We get that the average over S of the entropy of XS is greater than or equal to the average over S of this expression here, which I can shorten to say it's the sum over all I that belong to S of H xi given x less than I. And I'll do another interchange of variables. I'm going to interchange this expectation with this sum. Sorry, not expectation of variables, interchange of summation. So this is a sort of summation normalized, and this is another summation. So that's going to be equal to the sum over all I equals 1 to n. And so how much is that going to contribute to this average? It's going to contribute precisely the probability that I belongs to S, because we choose S at random, and then it'll contain some i's and not other ones, and this I, each I will be included, it will be make a contribution with probability, the probability that it belongs to the random S. So I'll get, here I get probability I belongs to S, H, xi given x less than I. And now we'll use our hypothesis. These probabilities are all assumed to be at least mu, so that's greater than or equal to sum I equals 1 to n H xi given x less than I. And this you may recognize because this is nothing other than the entropy of x1 plus the entropy of x2 given x1 plus the entropy of x3 given x1 and x2 plus the entropy of x4 given x1, x2 and x3 and so on up to xn, which is nothing but our old friend the chain rule again. So that equals mu times the entropy of x. And that was exactly what we wanted to prove. So we now have finished the proof of Shearer's lemma. And as I said before, in the next video, we'll have some applications.